Chapter 4, Entropy, Section 4.4, Entropy change in reversible and irreversible processes. It's straightforward to calculate the entropy change of a system that undergoes a reversible process. This is the definition of entropy in thermodynamics. The differential of entropy is dq reversible over T. dq reversible is du minus dw reversible. dw by itself is negative p external dv, but now it's a reversible process, so p external is equal to p. Therefore, dw reversible is negative p dv. Negative dw reversible is positive p dv. Now we have this expression for the differential of entropy. U is a function of temperature and volume. Therefore, du is delta U over delta T under constant volume condition times dt plus delta U over delta V under constant temperature condition times dV. And this term is C sub V. This is because in an isochoric condition, delta U is equal to delta Q. Delta Q over delta T is C, the heat capacity. Now, what about this delta U over delta V under constant temperature condition? In Chapter 5, we'll be able to prove this is equal to T times delta P over delta T minus P for all substances. Now we have this du expanded into three terms. We replace this du with these three terms, and then we have only two terms left because this positive PdV, this negative PdV cancel. Now we have only two terms in the end. We have CVdT over T over here. That's from this term divided by T. And also we have this term, delta P over delta T under constant volume condition times dV. So it's from this times dV over temperature. So we have this. Again, PdV, negative PdV cancel. What if a system changes from its initial state to its final state in an irreversible process? Well, you simply forget about this process and design another process which is reversible, that connects the initial state to the final state. And then you use the same equation to compute the entropy change of the system. Why? Because entropy is a state function. The definition of ds is dq reversible over T. So if you see an irreversible process that connects the initial to the final state, that information is useless when we compute the entropy change of the system. Alright, we need to have this dq reversible. So we have to mentally design a reversible process that connects the initial state and the final state. And then we can use this equation. Alright, because of that, the entropy change is the integral of Cv dt over T plus the integral of delta P over delta T times dV. So basically, we just need to integrate this. That accounts for the temperature change. We need to integrate this. That accounts for the volume change. Again, when the initial and final temperature and volume are given, we use this equation. What if the initial and final temperature and pressures are given? Then we can use this equation. We have ds is equal to Cp dt over T minus delta V over delta T times dP, proven in the previous video. We just integrate this side, that accounts for the temperature change, and then minus the integral of this, that accounts for the pressure change. And also, I think we have proven this sum is equal to this difference. So this equation for ds and this equation for ds, they can be proven to be the same. They are equivalent to each other. Now let's look at one numerical example problem, 4.4.1. An ideal gas, 2 moles, expands reversibly in an isothermal process until its volume doubles. Calculate the molar entropy change of this ideal gas, and also calculate the entropy change of the surroundings of the system. Again, we'll just use this equation, alright, and because I think we're given information about temperature and volume. Temperature, isothermal, there's no temperature change. This dt is 0. Therefore, we just need to look at one term. Over here, pressure is doubled. So we just need to integrate this. How can we integrate this? First, it's an ideal gas. So delta P over delta T is equal to nR over V for an ideal gas. It's just simple derivative problem. And then we can replace this derivative with nR over V, and then we can integrate this nR over V dV. And since the question is asking about the molar entropy, so we're going to have this divided by N, and we have this R times Ln2. Why Ln2? It's the natural logarithm of volume, and the volume doubles. So V final over V initial is 2. So we have this, R is 8.314 times Ln2, we get 5.763. Yeah, the unit is joule per Kelvin mole. Since the amount of the ideal gas is 2 moles, we can also compute the entropy change of the gas. Just 2 moles times the molar entropy change, we get 11.53. What about the entropy change of the universe? It has to be 0 because this is a reversible process. Alright, in a reversible process, the entropy change of the universe must be 0. And therefore, we can just write out this equation. Delta S plus delta S surroundings has to be 0. Therefore, delta surroundings should be negative 11.53. Or we can calculate the entropy change of the surroundings this way. We'll use the definition of entropy. ds is equal to dq over t. So delta S of the surroundings is the integral of dq surrounding over t. And dq surroundings is negative dq, alright? And then dq is du minus dw. Now we have this, and because du is 0, why? Isothermal ideal gas, therefore du has to be 0. We get this equation, and dw is negative p external dv. However, it's a reversible process, so dw can be written as negative p dv. So we have this, and the pressure over T is nR over V, and then we just need to integrate this. In the end, we get negative nR Ln2. So over here, delta S is positive nR Ln2. For the surroundings, the entropy change is negative nR Ln2. The sum is 0. The entropy change of the universe is 0. That means this process can be reversed without violating the second law of thermodynamics. Now let's look at a different numerical problem. Now this ideal gas expands against vacuum until its volume doubles. We're going to calculate the molar entropy of this ideal gas. Alright, this is an irreversible expansion. So we cannot just say, well, ds is equal to dq over t, because the definition of entropy in thermodynamics is dq reversible over t, and this is not a reversible process. The expansion against vacuum is not a reversible process because P external is 0 and the system pressure is greater than 0. P external is different from P. So we cannot compute entropy directly based on the information given from this statement. What we have to do is we have to design a reversible process that connects the initial state and final state. So if we look at the final state, the volume has doubled. What about the temperature change? The temperature change is 0, only because this is an ideal gas expands against vacuum. We cannot have heat flows into or out of the vacuum. We cannot do work to the vacuum. So during this expansion, there's no change in the internal energy of this gas. Alright, du is just 0. dw is 0, dq is 0. Alright. So because of that, there's no temperature change in this ideal gas. Why? Because if there's no internal energy change and there's no potential energy change for this ideal gas, therefore there's no kinetic energy change. The temperature is constant. Alright, so we have T final equals T initial, and V final is equal to 2 times V initial. So if you really think about all those changes from T initial to T final, V initial to V final, it's actually exactly the same as this. If you just look at the initial and final states, the numerical problem 4.4.1 and the numerical problem 4.4.2, they share something in common. They have the same initial states, they have the same final states. So really, we do not have to do any numerical calculations for this problem. we'll just design a reversible process that connects the initial state and the final state. This process is isothermal, reversible, and in the final volume is 2 times the initial volume. The final temperature equals the initial temperature. Alright, so we can just borrow the result from this numerical calculation. We get delta S is just this, and we have delta S molar entropy change, which is this. Again, the molar entropy change of the system is R times Ln2, and the entropy change is Nr times Ln2. Alright, so we'll just use the same result. We can get the molar entropy change of the system. It's just R times Ln2. We get 5.763 joule per mole Kelvin. Alright, another numerical example problem, 4.43. 2 moles of ideal gas expands against vacuum until its volume doubles. Now this time, let's calculate the entropy change of the universe. When the gas expands against vacuum, we know P external is 0 and P is greater than 0. So it is a irreversible process. Therefore, the entropy change of the universe must be positive. Now we're going to verify that. First, let's look at the entropy change of the system. Again, when we look at the entropy of the change of the system, we have to do the calculation not based on this information. What we need to do is we need to mentally design a reversible process that connects the initial state and the final state. The initial state and the final state, they differ in the volume. The volume has doubled. However, they have the same temperature. Again, it's just because there's no change in internal energy or kinetic energy. Therefore, there's no change in temperature. Alright, so we can still use this equation. Again, we're assuming that a reversible process has been mentally designed to connect the initial state and the final state of the system. And because dt is 0, we have only one term, and then this delta P over delta T is Nr over V, so we can easily compute this delta S. It's 11.53 joule per Kelvin. Now, what about the surroundings? Because the ideal gas expands against the vacuum, nothing can be done to the vacuum. Therefore, nothing has changed to surroundings. The entropy change of the surroundings is exactly 0 because it's surrounding the system. There's a vacuum and there's no change done to the vacuum. That's why. And what about the entropy change of the universe? Well, the universe is the system plus the surroundings. Therefore, the total entropy change of the universe is delta S plus delta surroundings, and now we get a positive number. And remember, as long as the change of the entropy of the universe is positive, it cannot be reversed. Because if we were able to reverse the process, the entropy change of the universe would be negative 11.53 joule per Kelvin. That means the entropy of the universe would decrease, and that's a violation to the second law of thermodynamics. We cannot do that. Now again, just to summarize reversible versus irreversible. In a reversible process, the entropy of the universe remains constant, and that's why we can reverse it. In an irreversible process, the entropy of the universe increases. That's why we cannot reverse such a process. And again, the total entropy change of the entire universe is the entropy change of the system plus the entropy change of its surroundings. When we calculate the entropy change of the system, you may just focus on the initial state of the system and the final state of the system. For example, if you know the initial temperature, final temperature, initial volume, and the final volume, you should be able to calculate the entropy change of the system. You can ignore any information about the process. Whether it's reversible or irreversible, just ignore this process. You just focus on the initial state and final state. And again, this is just because entropy is a state function. For the same reason, to calculate the temperature change of water, you just need the initial temperature of the water and the final temperature of the water, right? You do not need the information about the process between the initial temperature and final temperature. Delta T is just T final minus T initial. Temperature is also a state function. hopefully by looking at this analogy, you should understand when we calculate the entropy change of the system, we just need to focus on the initial state of the system and the final state of the system. However, when we calculate the entropy of the surroundings, there's something slightly different. We should always use this equation. In this equation, we're going to assume this Q of surroundings is always reversible. So that means when we calculate this ds surroundings, we should use the definition of entropy, which is dq surroundings reversible over T surroundings. However, because the surroundings is infinitely large, this is the rest of the universe, we're going to assume whatever happens to the infinitely large surroundings is reversible. And therefore, we can simply just drop this reversible, because any dq surroundings is dq surroundings reversible. So we have this. Now dq surroundings is negative dq, right? So again, dq surroundings is equal to negative dq. We have this because we're assuming q of surroundings plus q is always 0. That means we're just assuming q of the universe is 0. There's no heat flows in or out of the universe. So this is where this equation comes from. And now we have this equation. We have negative dq over T surroundings. We always use this to calculate the entropy change of surroundings. Now we integrate both sides. Delta S surroundings is the integral of dq over T surroundings. Again, T surroundings is the temperature of the surroundings, but for convenience, you can also say it's the temperature of the immediate surroundings. Alright, because again, the surroundings is infinitely large. If you have a bottle of water and the moon is part of the surroundings of the bottle of water, and the temperature on the moon is totally different from the temperature of the immediate surroundings of your water bottle. So that's why it's just reasonable to just use the immediate surroundings instead of the temperature of the moon. And in this equation, we made a big assumption, which is this: we don't care if the process is reversible or irreversible to the system. Okay, it's always reversible or considered reversible for the surroundings. So we can always use this equation. And dq surroundings is always equal to negative dq. Again, we're assuming dq of the universe is always 0, and therefore we can go from here to here. Alright, so now this equation is always used to calculate the entropy change of the surroundings. Now let's look at one more numerical example problem, 4.4.4. Let's look at this 20-liter ideal gas with 4 bar pressure expanding to 80 liters against a P external equals 1 bar at constant temperature. It's isothermal. And if you look at this, P is 4 bar initially, P external is 1 bar. Therefore, there is a finite difference between P external and P. We know this process is irreversible. And also, we know it's constant temperature. Therefore, du is 0 for this ideal gas. Alright, because it's an irreversible process, we know the entropy change of the universe is greater than 0. And also, we can quantitatively calculate the entropy change of the universe. So first, let's look at this delta S surroundings. When we look at delta S surroundings, again, we'll just use this equation. This is the integral of negative dq over T surroundings. Because it's an isothermal process, there's no change in temperature of the system, and therefore we can assume T surroundings is equal to T. Otherwise, there's going to be some temperature change to the system inevitably. So we'll have to assume T surroundings is equal to T, so we get this equation. And because T is constant, so it's just T on the bottom. On top, we have integral of dq, so that's just negative q. Negative q is W minus delta U, and we have this equation. Delta U is 0 because it's an ideal gas and it's isothermal. So we have W over T. W is negative P external times V final minus V initial. This forms the work equation. You know, work is equal to the integral of negative P external dV. So over there. And P external is equal to P final, because this system will expand until P final is equal to P external, which is 1 bar. So I'll just replace P external with P final over here, and now we have this expression. And it's actually hard to compute this directly. Right now I'm gonna just try to get the common factor, PF VF over T. So we have PF VF over T. Alright, so this is why there's -1 here. Obviously this is different from PF VF over T. It's PF VI over T. So this term is PF VF over T times VI over VF. I'll let you verify this multiplied by this is just the first term. The reason I do this is because PF VF over T is simply NR. It's just that we have an ideal guess, so PV equals NRT. T never changes, so PF VF is equal to NRT. And this is just NR. What about VI over VF? VI is 20 liters, VF is 80 liters, so we plug in this equation, and we have a quarter -1, which is negative 0.75 NR. I mean, it's fairly easy for you to just plug in, the values of N and R to compute this. But I think this is good enough to answer this question. For the system, however, when we calculate the entropy of the system, we'll have to just focus on the initial state and final state, because this is a irreversible process. This information is useless. We have to focus on just the initial state and the final state of the system, because entropy is a state function. And for a reversible process, we'll just use this equation because temperature is constant. So we have this expression. When we have this expression, we have NR over V because it's an ideal gas. We'll just integrate this, which is NR times Ln4. The reason is very simple. LnV final minus LnV initial is just Ln4 over here, and we get a positive expression for the entropy change of the system. So when this system expands in this irreversible process, the entropy change of the system is positive. The entropy change of the surroundings is negative. They do not cancel. They do not cancel. We sum it up, we get a positive number, positive 0.636 NR. This is greater than 0. That's why this process cannot be reversed, because the reversal would violate the second law of thermodynamics. Another numerical example, 4.4.5. So now we have a 20 liter ideal gas expands to 80 liters against P external equals P. So when you look at this, you know it's reversible, and you know the entropy change of the universe should be 0. So if you don't do any calculation, you just say the entropy change of the universe is 0, it's actually correct. But we can also calculate the entropy change of the surroundings. We can also calculate the entropy change of the system. First, let's calculate the entropy change of the surroundings. It's the integral of negative dq over T surroundings. Because it's an isothermal process, T surroundings is just T. And we have negative dq. Okay, we can integrate that. We get negative q over T. It's W minus delta U. Delta U is 0, so we have delta W over T. W is negative integral P dV, and P is nRT over V, and then we have all this. The surroundings has an entropy change of negative NR Ln4 in the end. Now, what about the system? Again, we're going to use this equation. We mentally design a reversible process. Well, it happens this is already reversible, so we'll just use this equation. There's no temperature change, so we just integrate this dV term, and delta P over delta T is NR over V for an ideal gas. We integrate this, we get NR times the natural logarithm of V final over V initial. This is NR Ln4. So for the surroundings, the entropy change is negative. For the system, the entropy change is positive. For this problem, they cancel. The entropy change of the universe is exactly 0. Now let's look at the entropy change of a liquid or a solid. We can calculate the entropy change using either of these two equations. So both equations are correct. This equation is used when temperature change and volume change are given. This equation is used when temperature change and pressure change are given. Now delta P over delta T can be proven to be alpha over kappa. What is alpha? Alpha is actually delta V over delta T on a constant pressure condition and then divided by V. What is kappa? Kappa is defined to be a little bit different. It's actually negative delta V over delta P under constant temperature condition divided by V. The reason we have negative sign in the equation of kappa is to ensure the numerical value of kappa is always positive. Alright, kappa is compressibility. Alright, this is how the relative volume changes when the pressure changes. Alright, alpha is how the relative volume changes when the temperature changes. Okay, now we have this equation, and delta V over delta T is simply alpha times V. So we have these two equations. The reason we rewrite those derivatives in terms of alpha and kappa is because for a liquid or a solid, the values of kappa and alpha are approximately constant within a moderate temperature change and a moderate pressure change. So it's just very convenient for us to plug in the values of alpha and kappa here and here. Alright, numerical problem 4.4.6. Calculate the molar entropy change of copper when its temperature changes from room temperature to like 26 degrees Celsius, and when the pressure changes from 1 bar to 2 bars. We have the density of copper, we have alpha and kappa of copper, we have CPM of copper, we have a lot of information. So now we have pressure change. So let's look at this. Let's look at this and this. These two terms have physical meanings. Over here, this is the molar entropy change under isobaric condition. This is molar entropy change under constant temperature condition. So first, let's look at this one. This is molar entropy change under isobaric condition. So we have this term over here, this term over here. Plug it in. All right, they just differ by the number of moles. We plug in all the numbers, we get this much. Now over here, what if temperature is held constant? And then we need this second term, negative V alpha dP. So we plug it in here. Again, these two just differ by the number of moles. And what's the molar volume? It's this one. Molar volume is just molar mass over density. That's molar volume. All right, molar mass over density, you get molar volume. And then you have alpha over here, and then you have pressure change over there. We get this one. Now let's compare this number and this number. I think this number is so much bigger than this number. This is 10 to the power of negative 2. This is 10 to the power of negative 5. Over here, temperature changes. Over here, pressure changes. So really, entropy depends much more on the temperature change than on the pressure change. Alright, but still, what's the total molar entropy change? We just sum it up. This is due to the temperature change. This is due to the pressure change. We sum it up, we get this number. The entropy change of a liquid or a solid may be calculated using either this equation or this equation. Either way, I mean, just based on the information you're given. If you are given temperature and volume, use this equation. If you are given temperature and pressure, use this equation. Alright, so now another numerical example 4.4.7. Calculate the molar entropy change of copper when its temperature changes from this to this. We have pressure change from this to this. The density of copper is this, and we have alpha and kappa. And now this time we have CVM of copper. Alright, not CPM, we're given CVM of copper. So somehow it's a little different from the previous example. In the previous example 4.4.6, I'm going to show you, we're given CPM. Over here we're given CVM. Alright, and now let's calculate the entropy change. So there are a bunch of ways to do the calculations. One way is to compute CPM given CVM, and then we're gonna just do this. Alright, just like in the previous example, all the same calculations except one thing. From CVM we compute CPM. But another way is this. We can use this equation instead. We can get the temperature change, and also we can get the volume change, and then we integrate this part, and then we integrate this part. Alright, so first let's look at this. In this equation, we have molar entropy change under constant volume condition. That's why we can use CVM over here. We have CVM over here, and then logarithm T final over T initial. We get this number. This is the entropy change of the system because due to the temperature change under constant volume condition. Now let's look at how the entropy changes when the volume changes. First thing, we need to calculate the volume change. How does the volume change? The volume depends on the temperature and pressure. So this will give you the relative volume change multiplied by molar volume. We'll get the absolute volume change. And why is this a relative volume change? Remember alpha. What is alpha? Alpha is delta V over delta T divided by V. What is kappa? Kappa is negative delta V over delta P divided by V. So that's why over here the first term will give you the relative volume change due to temperature change. The second term will give you the relative volume change due to the pressure change. So we need to sum it up, and then we get the molar volume change. It's a very small number in cubic meter divided by mole. Now we can compute this. We have alpha, we have kappa, we have delta V. Where does this come from? It comes from the second term over here for the differential of entropy. Alright, we just plug in on the numbers, we get this. So if you compare these two numbers, again, the entropy depends more on the temperature change, less on the volume change. But still, we can sum it up, and we get the total entropy change per mole of the substance. And it's 0.08186. If we look at the previous example, 0.08184, and if you really think about it, the initial and final states of this numerical problem and the initial and final states of this numerical problem, they are actually the same. So supposedly we get the same result, and indeed we get the same result. Only the last digit differ. It's just some like numerical inaccuracy. So really important for us to realize that this equation is exact for all substances. This equation is also exact for all substances. Which equation should we use? We can use either one. But we need to examine the information given to us and use the equation that's more convenient. You know, if we're given the temperature change, pressure change, and if we are given CPM as well, we definitely use this equation. What if we are given the temperature change, the volume change, and CVM? We definitely use the first equation. What if we have only CVM and then pressure change? Okay, somehow we can calculate CPM given CVM, or somehow we can just compute the volume change, alright, given the temperature change and pressure change. Either way, we should be able to get the same results if we are starting from the same initial state and same final state, only because, remember, entropy is a state function. The change of the entropy of a system is simply the final entropy minus the initial entropy, which does not depend on the process. So that's why you can use this equation. You can use this equation over here. We just look at how entropy changes with temperature when the volume is constant, and then how entropy changes with volume when temperature is constant, and then we sum it up. Over here we just look at how entropy depends on temperature when pressure is constant, and then how entropy depends on pressure when temperature is constant, and then we sum up this to delta S. And either way, you should be able to get the same numerical value like I showed you here, 0.08186, and over here 0.08184. Okay, they are essentially the same.